Okay, welcome. It's a great pleasure for us to have Yimu Bao as our speaker today. Yimu is currently a postdoc at KIPP. Uh, Yimu has been doing a lot of interesting work at the intersection of quantum matter and quantum information. In particular, in the past, he did very influential work on monitored quantum circuit dynamics and also uh, how robust the topological quantum memory is under various open system dynamics. And today he's telling us something new about designs in magic augmented circuits. Im, please go ahead.
Hey, thanks, Liu for inviting me to speak at this seminar series. Yeah, today I'm going to tell you about a recent work we posted two months ago about designs in magic augmented circuits. This work is in collaboration with Yu Zhen, who is a grad student at UCSB. Sarga is a faculty member here, and Yingfei, who is at Tsinghua IAS. Um, so to get started, random unitary is has a lot of application in quantum information science. Uh, per, Probably for everyone who wrote a numerical program for Monte Carlo simulation have used a function called random number generators. Assume that you have a quantum computer. One of the function you would like to have is a random state and a random unitary generator. And indeed, random unitaries has many applications in the near-term quantum information processing task. For example, there's a type of Google use this um, Google use the random circuit sampling to demonstrate the quantum advantage in their quantum simulation platforms over 60 qubits a few years ago. And also random unitary has applications in shadow tomography, which is an algorithm people use to try to learn the observables in quantum states. Also, random unitary have application in doing randomized benchmarking. This is important for the experimentalists who want to benchmark the fidelity of their gate. However, generating a random unitary over a many qubit system is a very challenging task. So suppose you have a n-qubit system and you want to generate a random unitary over the entire system. The Hilbert space of this system is exponential in system size. So that means a random unitary over an n-qubit system will have exponentially many parameters. That means that just by parameter counting tells you that if you want to write it down as a circuit that consists of two qubit unitary gates, that requires exponentially many gates and applied in in a depth that is exponential in the system size. So this is obviously a very challenging task. However, uh, we don't usually need a exact random unitary over a very large system. Usually, in many cases, approximate random unitary is often enough. To say what counts as approximate random unitary, we need to just take a step back and think about in which cases we are going to use this random unitary. So there's a way um, to at an abstract level to describe the experiment or the algorithm we are going to run on a quantum computer. Broadly speaking, the most general one, people call it adaptive experiment. In this experiment, you may want to use a random unitary U in this purple box for many times in somewhere in your circuit. And and these U are generally inserted at different time step, and they cannot be they can and in between different application of U, there might be some generic gate. I call it W. And in this experiment, people call it adaptive experiment. So the goal to you have the goal to come up with an algorithm that generate random approximate random unitary is that you hope um, if you have say you have an ensemble of unitary U, and when you draw this random unitary from your ensemble rather than the genuine hard random ensemble, you want to make sure that the output state of say a adaptive experiment, I call it A, has an output state that you cannot distinguish from the output state that you query a genuine hard random unitary. There are another more restricted set of experiment. People call it parallel experiment, in which you query this unitary U for k times and apply them at the same time step. I want to make it clear that here, when I say I query a random unitary U for k times, I mean I draw a random unitary U from an ensemble and use the same unitary U for k times. Um, okay, and
Sorry. Question.
yes,
In
yes,
the
please.
previous
Mhm.
equation, what is that A?
Oh, A is the circuit that I wrote here. For example, on the left is the adaptive circuit that consists of this random unitary and some generic other unitary operation. I call it W.
I see.
So everything together, I call it A.
But in this equation, you are not taking any average, or are you taking any
No,
average?
no, no. I'm not taking any. I'm not.
Okay, then this U from the ensemble epsilon and the U from the Haar ensemble, what's the relation between them?
Here. Okay, okay. Yeah, yeah. Yes. Sorry. So this in this equation, yes, I want to put an average on the um. Let me say this. I want to put mm, yeah, I want to put an average on the yeah, I want the average trace distance to be small. So here, you from ensemble and you from hard, it just means when I run this algorithm, I draw U from the ensemble E, or U is drawn from a hard random ensemble.
I see. So then you first calculate the trace difference and then take the average.
Um,
Or you first take the average and then calculate the trace difference?
let's see, let's see. Yeah, I first take the average and then consider the trace distance. Sorry, yeah, yeah.
I see. Mhm.
Okay.
Okay.
I have another question. Excuse me.
Yes,
So
yes. Hmm?
in this slide, do you allow to consider circuits with U dagger?
No, no, I'm not allowed.
Oh, not allowed. Okay. So for example, for the shadow tomography, uh, you need to do some uh, reconstruction. Is that also included in this equation? And
Uh, do some reconstruction. Let's
yeah,
see.
after measurement, you reconstruct the original state using
No, 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 no,
somehow
no.
using U dagger, right?
Um, no, 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 no. That is not. So here the circuit has to be unitary. So I'm only considering unitary circuit. A is a unitary circuit. It doesn't have
Okay.
any measurement.
So this equation itself does not guarantee the validity of classical shadow tomography. Does this mean that?
Yeah, 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 yeah. This equation itself, no, 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 it does not. Yeah, the task of
Mhm.
shadow tomography, you require measurement.
Okay, thank you.
Okay. Yeah, that's our goal. And so one concept that guarantees that will actually I will show in a moment that will guarantee good approximation in the quantum experiment I mentioned before is this concept called K-design. The K-design is a concept that regarding the statistical property of an ensemble of unitary or ensemble of state that I'll talk about later. Let's say consider an ensemble of unitary for now. We can define a object. I call it k-fold quantum channel. That is the that is the that is the following object that I consider the unitary operation U acting on k identical copy of the Hilbert space, and I ask what is the average action of this U to the k. And the ensemble forms an exact K design if this K-fold channel, which is the average quantity over the entire ensemble, agrees with the result that comes from a Haar random ensemble. And there's a well-established notion called approximate K design. And there are different measures of how good the ensemble of a this unitary ensemble is a K design. For example, one quantity people use a lot is so-called relative error. A design forms a an ensemble forms a K design with epsilon relative error if the following condition holds. So what does it mean? You should interpret this equation as, oh, actually, can you see my cursor on the screen? Probably not, right?
No.
Okay, so this equation, uh, okay, never mind. So this equation, 1 minus epsilon times phi har less or equal than phi epsilon just means the right-hand side minus the left-hand side is a completely positive map. No matter what input state you send into this channel, and what whatever positive operator you measure in the output state of this k-fold channel, the right-hand side will always be greater than the left-hand side. That's the first arrow. That's the second line here. That's basically the very meaning of this is semi-definite ordering. And if this relation is satisfied, people call this ensemble epsilon forms a K design with epsilon relative error. Okay, this relative error K design actually will guarantee a bounded additive error bounded trace distance in the adaptive experiment. That means if I have an ensemble that forms an epsilon relative K design with epsilon relative error, then I can use this ensemble in the adaptive experiment. My output state won't be very different from the state that I obtain if my unitary is drawn from the completely Haar random measure, drawn from the Haar measure. Okay. Another notion of the errors in K design is so-called additive error. In this case, it's just the K-fold channel associated with the ensemble of unitary has a bounded diamond norm with the channel associated with Haar random unitary. In this case, it bounds. Okay, this small additive error means no matter input state you send in and whatever operator you measure in output state, the expectation value will be very close. This measure will actually guarantee that if you run the parallel experiment that queries n copies of unitary like in a parallel way, then the output state are close in trace distance. Okay, these are the well-established measure of how good a ensemble forms a K design, and people have established some rigorous result in the past, I would say, 15 years. One seminal work was done by Brandao, Harrow, and Horodecki back in 2012. They show that if you have a random circuit of consists of two qubit random gate, and if the depth is n times k to the 11, then this random circuit actually forms forms a forms a forms a unitary K design up to epsilon relative error. The epsilon dependence is just it actually comes into the depth as a log 1 over epsilon factor times n and k to the 10, but that is not so important. This result has been improved in the next decade, and was, I think, eventually people shown that in basically just by improving their proof technique, shown that in 2024 that you don't actually need a very bad scaling with respect to k. They improved the scaling with k from k to the 11 to linear in k. Really a breakthrough result actually also happened later on last year by Schuster, Haferkamp, and Huang. They actually managed to show that you don't really need a linear in n circuit depth in order to prepare a K design. You actually only need the log depth. Um, uh, I should say that all these I'll tell you a little bit more about the latest breakthrough work later on in the talk. But I should emphasize that all these work actually were focusing on the the random circuit that consists of two qubit hard random gates, and the improvement in the result is only because people use a better proof technique that were able to show the sufficient that a lower depth is sufficient for relative error K design. There's another line of thought. People thought like if you use two qubit hard random gate, that is actually still not so realistic for near-term quantum devices, and especially if you want to implement if you actually run your device at the um, if you want to run a quantum circuit at the logical level of um, of a near-term device, let's say each logical qubit comes from a 2D surface code, then it's not so realistic to implement a generic two qubit gate. It might be more realistic to consider a circuit that consists consists mainly of, say, a Clifford gate, which is easy to implement, say, in a 2D surface code, and only use magic gate, which is a jargon people used for non-Clifford gate, for a few times somewhere in the circuit. Inspired by this, along this line, there's great work by Haferkamp and collaborators in 2020. They show that if you consider a circuit that made of global Clifford gate over n qubit, and followed by a single qubit non-Clifford gate, can be T gate or hard random gate, and repeat this pattern for many times, you only need n times k number of magic gate to realize the relative error K design, and only need a actually system size independent number of magic gate to realize a additive error K design. However, this circuit is inherently like deep in the sense that the circuit depth is linear in n. And it's even worse. It's actually proportional to n squared for the relative error K design construct. So motivated by all this work, we were trying to come up with a way to reduce the usage of try to come up with a shallow circuit that can construct K design, and at the same time use somewhat a smaller number of non-Clifford gate. So the goal is just to minimize the circuit depth and the usage of magic gate simultaneously. So here is an outline of today's talk. I'm going to tell you about our construction of relative arrow design and additive arrow design. The take home is we actually managed to get a construction of relative arrow K design with an improved circuit depth. And for the additive arrow state design, we actually managed to get a construction that only use order K square number of magic gate that does not depend on system size, while uh, in this and at the same time use a circuit that is shallow in the sense that circuit depth is log n or even log n in the case we have long range connectivity. Okay. So first let's go to the first part. So the first I want to tell you a little bit about what is our construction and what is our result. So, our construction of this K design with relative arrow is using this circuit. We call it magic-augmented Clifford circuit. So the circuit is made of mainly Clifford gate, and only introduce magic gate before and after the Clifford gate. So for example, this is the picture here is an example of this magic augmented Clifford. And we managed to show that such a circuit with a two-layer Clifford structure and each block of Clifford gate acting on log n number of qubits. Um, Before and after this two-layer Clifford, we applied this constant size magic gate, which is drawn from an exact K design. So you should think about this purple gate at the beginning and the end of this circuit is you can for now you can think about them as a high random gate over a cluster of qubit, and the qubit cluster is of size k times log k. And we managed to show this can realize a K design with epsilon relative arrow. And this construction has this construction has a very appealing property. First of all, it use a limited number of magic gate, of course, and also actually has a rather shallow. The depth is very small. So the circuit depth is in this case is order log n plus a function of k. So the first part comes from the depth of Clifford because we have a Clifford gate over log n number of qubits, and we use the fact that any Clifford gate over log n number of qubits can be implemented in log n depths without any prefactor. So that's the first part of the circuit depth. And second part, two to the k log k is just the circuit depth to realize a exact k design over small qubit clusters. If you and for Clifford gate, there's actually another appealing property, which is that if you are allow all-to-all circuit connectivity and using a lot of ancilla, you can further compress the depths of this block size Clifford gate, like a green gate in this diagram to a depth that is log of the size of the qubit block, which is log n in the with n being the total system size. That actually allows us to have a construction that is really shallow. If you care about only the K design for small k that does not scale with system size, our circuit depth is actually just log n, which um, which I was told that many Russian physicists would call log n a constant. Um, okay. And just as a comparison to the results that from last year by Schuster, Hefferkamp, and Huang, they used the two-layer. We are using a similar circuit construction. However, they're using the cube the unitary in their two-layer circuit is actually approximate K design. That actually require the depths of that unitary block to be a two-qubit unitary circuit of depth that is linear in K. So that leads to a scaling that is K times log n in their construction. However, our result have a because we use mostly the Clifford gate, the depth it becomes a log n plus a function of K. So the depth actually improves their result in the case that K is constant. Furthermore, we have a construction. We can even compress the depth if you allow all-to-all connection. That's another benefit compared to their result. Okay. So now let me just walk you through a little bit about how we prove this result and what is the physical understanding based on the statistical mechanics. Um, to start, what is our goal? So our goal is to show that maybe I write it here. Our goal is to show that this k-fold channel is similar to the k-fold channel of a global Haar random unitary. So let's think about what is the k-fold channel of a global Haar random unitary. Here I'm just using using the result that people use all the time about averaging over k copies of Haar random gate, and that actually can be written as a summation over a few terms, and each term is labeled by an element in the permutation group. This is this result. If you want to physically understand it, it just says, say if you consider every average of k-fold Haar random um, k copies of the Haar random unitary, what will left after the averaging is an element in the commutant of tensor power of Haar random unitary, and that commutant only consists of element that give labeled by the permutation. So this is uh, and diagrammatically one can write down this average this k-fold channel associated with Haar random unitaries in the way that is shown on the right. Here we sum over sigma and tau belong to a permutation group, and sigma and you can there is a I call this sigma and tau a permutation spin, and each one actually specify the action in the output or input of this quantum channel. Because here in the average expression that I have, R of sigma is an operator associated with sigma, which will left after averaging, and R of tau is something you compute on the input state. There's a important property actually that allows us to simplify a lot of the proof, which is this channel is you can take the diagonal approximation of this k-fold channel, and the approximation error will be exponentially small in the system size. So you can approximate it, just drop the term that sigma is not equal to tau. So this reduces the problem of proving that there's a small relative error comparing k-fold channel of our ensemble to Haar random k-fold channel. Reduce that problem to comparing this phi epsilon to phi a, which is the diagonal approximation of phi Haar. Right, and this is also what Schuster, Haverkamp, Huang used in their work. The key part of their proof, which is also key part of our proof, let me explain here, is something called the gluing lemma. The gluing lemma is the following, which says if you have a Haar random unitary acting on system A and B, followed by a Haar random unitary acting on system B and C, if the overlapping region B is large enough, actually uh, if when you combine this UAB and UBC together, it forms a random unitary over the entire region ABC. The point is, form over the entire region ABC with a very small approximation error epsilon. In fact, this overlapping region, which I call B, only needs to contain log k over epsilon number of qubit. So there's a really simple statistical mechanics understanding of this gluing lemma, which is essentially what physicists would call a pious argument. So just think of take the diagram on the left. We have two channel AB, phi AB, phi BC, and after averaging, they become summation over some permutation spins. And there's a property that one should know, which is when sigma and sigma prime are not equal, when you contract this two channel, it will actually cause a suppression in the weight of that curve. So the contraction between sigma and sigma prime will favor the configuration that they are aligned. So here you can basically ask whether the gluing lemma is basically saying that whether I can approximate the summation on the left as the summation on the right by throwing away all the configuration that sigma and sigma prime are not aligned. Um, this is very similar to what we do in statistical mechanics every day. And for the configuration that sigma prime are not aligned, there's suppression in the weight given by 1 over dimension of the subsystem B. So that you can view it as energy cost of log of dB, which is the size of B. And you can also ask what are the number of configuration that sigma and tau are not aligned. By the way, when they are not aligned, the suppression in weight also depends on the distance between sigma and sigma prime in terms of the number of transpositions, which is the way you define distance between two permutation elements. And the elementary domain, or which are when sigma and sigma prime differ only by one transpositions, are only have k squared numbers. So that leads to an entropic term that is log k squared. So by this simple argument, it already tells you that the configuration with a domain will get suppressed if B is larger than, say, log k squared over epsilon. Um, so basically, if you apply gluing lemma for many times, so that tells you that gluing lemma is basically says if region B is large enough, then there's no domain wall. And you can imagine if I choose the overlapping region between these two layer hard random unitaries to be large enough, actually you can ensure that these spin variables arise from averaging over hard random unitaries in every gate in this two layer circuit will actually align if I choose the overlapping region to be large enough. So what is needed here is just so every time you glue, you produce an arrow that is epsilon. Now you glue it for n times to basically connect all the gate in this two layer circuit. You just need every time when you glue, you have an approximation error that is epsilon divided by n, which basically says the overlapping region needs to be log of system size divided by epsilon. If that is satisfied, then you know that in this spin picture, all the spin are aligned, and the two layer hard random unitary will behave like a global hard random unitary. This is basically the understanding of their result. And in this work, we are considering majority of this two-layer structure in our construction is not hard, but it's Clifford. However, Clifford has a rather similar average. Random Clifford has a rather similar. The average of that has a rather similar structure compared to the hard random unitary. The only difference is when you average, you're not only producing the element labeled by permutation, but you have more element. That is it's just that just mathematically that just means the operator that commute with all the Clifford tensor power is just strictly more than the operator that commute with generic tensor power of generic unitary. This leads to a leads to a leads to a this just leads to the result that Clifford Compton has more operators, and you need a spin variable, I call it T, that contains more contain more than permutation spin to label the result after averaging. Um, However, all the other things are pretty similar to the permutation spins, and this operator in the Clifford commutant T also you can define a distance between them, and the contraction between different variable T will favor the configuration when they are aligned. When they are not aligned, they are suppressed by similarly to the case of permutation, they are suppressed by a factor that is proportional to the that is one over the Hilbert space dimension. Um, okay, this allows us so this property actually allows us to show a similar result as the two-layer Haar. Here we can show the two-layer Clifford after averaging. You will get you can approximate this k-fold quantum channel for the Clifford by by mostly the uh the by mostly the aligned configuration plus some other configuration that this T spin T is coming from averaging over Clifford that have spatial fluctuation. We propose a condition, we call it uniformity condition. Basically says whether the whether the configuration that are not just to count the weight of the configuration that are not perfectly aligned is sum of these f coefficients. If they are less or equal than epsilon, we call the Clifford circuit to develop an approximate uniformity, and we can show, and similar to the case of Haar random unitary, this uniformity condition can be achieved when the overlapping region is of log n size. Um, yeah, and the way this uniformity is developed, you can also you can also use the similar picture I explained before. You can treat by treating this spin this classical variable t coming from arising from the Clifford average as a classical spin, and this spin has some if they are anti-aligned, there's an energy cost, and there's uh, and then you when they're anti-aligned, there's an energy cost, and there's a entropic term associated with where are those where those domain work can occur. And it's basically also a simple Pios argument counting. You can show that when the overlapping region is log n, the you will actually develop all the domain will suppress, and you will the k-fold channel will satisfy the approximate uniformity. Just to make a comment that the, the here it's slightly different from the usual statistical mechanics analysis where people only care about the domain or that flips extensive number of spins. Here, in order for the k-fold channel to look similar to to this uniform piece in the Clifford circuit, or looking like, or to be approximated by the Haar random k-fold channel in the in the in in the Haar random case, that you need to suppress all the domain walls regardless of the system size. So that's a subtlety in this analysis, and we call the uh, we call this strong ordering in the statistical mechanics model, in the sense that there's absolutely no fluctuation. All the domain walls. The uniformity condition is equivalent to this strong ordering in the stack. Uh, okay, this uniformity condition is very useful, and that actually tells you once this Clifford circuit develop this uniformity, you can convert it to a Haar random unitary by adding small blocks of random unitary gate at the beginning and the end. So just to know that before you add this Haar random unitary gate, the k-fold channel of Clifford will contain was contribute the majority of the contribution comes from the uniform part, and for that uniform part, the spins are allowed to take all the take the value. The spin can represent every operator in the Clifford commutant. It can be either a permutation or the other operator that arise from the Clifford average. However, here the idea is if you sandwich this Clifford channel by two layer of hard random unitary, all the configuration that are not in the not that are not permutation will actually get suppressed because the hard random unitary at the beginning and the end after averaging only produce the spin uh, pr produce permutation spins. They will actually suppress the contribution in the Clifford that are not corresponding to permutation. This will allow you to convert the k-fold channel to the k-fold channel of hard random unitary. Um, okay. This is a bit technical. Let me skip this part. Okay. So the previous part I just explained that we have a construction of the relative error unitary design, and actually we also have similar to that we also have a relative. We can construct a relative error state K design. A state K design is an ensemble haven't introduced, which actually is a property associated with an ensemble of quantum state rather than ensemble of random unitary. Here, a state forms a K design is assessed that the case moment of the state ensemble, which is the average of K copies of your quantum state drawn from that ensemble, um, is upper and lower bounded in the operator sense by the case moment of a hard random state ensemble. This will guarantee that no matter what operator you measure in the whatever positive operator you measure in that in this case moment in this k-fold state rho epsilon k, it will have an expectation value that is very close within the multiplicative arrow epsilon to the observable expectation value you obtain in the hard random k-fold state. There's a associated notion which is the additive arrow state design that basically says that whether the k-fold state is close to the k-fold hard random state in trace distance, and that will guarantee the expectation value are close in magnitude. Similar to this construction of unitary design, we have this proposal for relative arrow state design. Relative arrow state design. So the construction is very similar, but the only difference is now we consider applying our two-layer Clifford circuit to a product state prepared in the computational basis, and now only after that we apply this block size hard random unitary, and this we can show using a similar technique, and this can achieve a relative arrow state design. Okay, before moving on, let me make a few remarks. First of all, our construction of state K design with relative arrow actually only consists of state with short range magic. Here, let me first define what I mean by short range magic. So in condensed matter, people are very familiar with short range entangled state, which are the state that can be prepared in a shallow depth local unitary circuit. And here we define the short range magic state by the state that can be that prepared by applying a finite depth local unitary to a generic stabilizer state. In other words, if a state can be converted back to a stabilizer state by applying FDLU, I would call this state having only short range magic. Um, okay. According to this definition, our construction of the state K design with absolute relative arrow only consists of such state because our construction is basically is applying a product of random gate to a Clifford to a Clifford state. Actually, in hindsight, this tells you that um, it's not that hard to construct a state K design with relative error because this state with short range magic they are just minimally different from the state from the stabilizer state in the sense that it's it, if you are allowed to change your local basis over a constant number of qubits, you can actually view this state as a stabilizer state in a different basis. Okay. Okay. The next thing we want to remark is that we actually have we not only have this construction of K design, we also have a few no-go. We also provide a few no-go theorems. The first thing is one might wonder now that you apply the magic gate only at the very last layer, can you actually generate a relative error K design by applying magic gate at the beginning, say in the construction of state K design? Actually, this is not possible in a certain sense. Here we show that if you consider this Clifford augmented MPS, so you can have a magic state represented by MPS as your initial state, and you are allowed to apply any Clifford operation to it. You can ask whether this ensemble of this Clifford augmented MPS can construct a relative error K design or not. It turns out it turns out not for a very small bound dimension. So if your bound dimension is is scales slower than system size to some power, then we can show you can never realize a relative error state design. This is because you can measure how much magic you have in the Clifford augmented MPS. One way to do that is just measure the stabilizer in entropy, and that will reduces to the stabilizer in entropy of the initial MPS because Clifford doesn't produce any magic. And you can show that this MPS with a small bound dimension, for example, a constant bound dimension that does not scale with system size, will have a will have a will have a much smaller will have will be different from the stabilizer in entropy in a hard random state actually in the subleading term, and that is already allowed to tell you that it cannot form a relative error state design. Um, oh yeah. So after our first version of this paper is out, actually, Yingfei sent our paper to Gemini 2.5 Pro, and it actually spotted a mistake we had in the small mistake in the early in the version one of our paper. So special thanks to our AI assistant. Okay, we also prove a few other no-go theorems says that if you start from a generic FDLU state prepared by FDLU in D dimension followed by Clifford that cannot generate a relative error state design, and also Depth local unitary preceded and followed by a Clifford gate cannot form a unitary K design with relative error. Okay, I think in the next 10 or 15 minutes, I will just talk about second part of our result regarding constructing the designs with bounded additive error. So here we will show that in order to generate state design with bounded additive error, we only need a constant number of magic gates. Okay, to briefly recap, what is state design with additive error? The definition just concerns about the k-folds, the average k copies of the state in this ensemble, and compare that to the state from hard random ensemble. Um, so the ensemble forms a state K design with epsilon additive error if this two k-fold state has a small trace distance, and this will guarantee that if you measure observable in this k-fold state, they are very close in magnitude. This also ensures that if you run a adaptive experiment that query random state for k times, any such adaptive experiment cannot distinguish sorry, any such adaptive experiment will have the same result if your state is drawn from your additive arrow state design compared to the situation that your state is drawn from a genuine hard random state ensemble. So our construction is again very similar to what we had before. Just the only difference is instead of applying a layer of magic state that acting on like an extensive number of qubits, we only require to apply constant number of single qubit magic gate to the output state of this two-layer circuit. Um, and this is already enough to achieve this additive state design. Um, Actually, so there's a concurrent work to our paper by a Caltech group, and they actually managed to prove a circuit depth lower bound for the additive arrow state design, and our construction actually saturates the optimal depth scaling. Um, right. So the proof is also rather simple. Um, so we just use the fact that this two-layer Clifford circuit can develop uniformity in the when each gate is acting on log a number of qubits. That will allow us to approximate the case moment of the state generated by two-layer random Clifford by the by the by the by the configuration that's represented by aligned spins, by spin aligned spatially. So this will allow us to approximate this k-fold state as a uniform piece given by this summation over T r of t, and the subleading term that has a spatial fluctuation in the configuration of t spins. One can show that once this qubit block has log a number of qubits, the deviation from uniformity condition can be bounded by epsilon. So this is good. So starting from this uniform condition, and you can ask how many single qubit magic gate you need to insert in the output in order to convert the convert the case moment of your state to the case moment of hard random state. In fact, this is again can be understood in the STEMAC picture because the case moment of a hard random state will be just given by a subset of this spin configuration T that correspond to permutation. And the magnetization and inserting a hard random or generic magic gate in the output is just imposing a energy. It's just imposing an energy cost to the aligned configuration T that does not belong to the permutation group. We know there are 2 to the order k squared such configuration, which gives the entropic term that's proportional to order k squared. That is to say, if you can insert order k squared number of magic gate, you can actually suppress the contribution from those non-permutation from those t spins that does not correspond to a permutation, and that which is enough for us to achieve a state k design. Okay. Okay, that's roughly the idea on how to prove this. In the very end, I want to note that we also have a construction for additive arrow unitary design. Okay, I forgot to put the definition here. So the definition is the k-fold channel associated with this ensemble has a bounded diamond norm distance from the k-fold channel of a random unitaries. Here, here we have this construction that uh, if you first apply a har here actually you just need to apply a unitary k design with epsilon additive arrow to a finite number of qubit an m that an m is order k to the order k cube. After this magic gate, you apply a global random Clifford gate. We are able to prove that this construction can produce a unit produce a unitary design with small additive arrow, and the circuit depth of this construction would be linear in system size, and you can further compress that to log n by using all-to-all circuit and then Ancilla, this similar trick that one can compress the Clifford gate. By the way, there's a concurrent work to ours. They show that the linear depth is required if we have a magic gate over a finite number of qubit. Um, so it is also likely if you restrict this if you only want to use a order one number of magic gate to in this construction, linear depths of the circuit might be required. I think it's required for this construction. So that is to say, our construction might also be optimal in some sense. Okay, that brings to the end of my talk. So I hope I convinced you that in today's talk, we, I present a construction of the relative error unitary design with improved circuit depth compared to the paper by Schuster, Haferkamp, and Huang. Also, we provide a construction of relative error state design using state with only local magic. Other than that, we have a construction of additive error state design in shallow circuit that using only constant number of single qubit magic gates. Besides that, I provide some statistical mechanics picture for understanding this result and some no-go theorem in constructing designs with bounded relative error. Okay, here are some outlook. First of all, there might be a potential improvement on our results. So in our construction, we use this block size Clifford gate over, block size random K design gate over order K log K number of qubits. This can potentially be improved. I think at this moment we require this number of gates. I think it's because of a lack of understanding regarding the structure of Clifford commutant. We have some discussion about this in the discussion section of our paper. And second is, I think Pengfei asked a question about whether I'm allowed to query a U dagger in my quantum experiment. So I'm not allowed in everything I talk about in today's talk. However, uh, you can ask what is the notion of, can you generalize the notion of K design to ensure that the quantum experiment which allows query U and U dagger cannot distinguish the ensemble from a hard random ensemble. This is a notion people call strong design, and in that case, you will have to require to construct a strong design using quantum circuit. You have to have a depth that is linear in system size. If you impose locality, and you have to be a circuit that's probably log, and if you allow all to all. However, in that case, there's still a question on whether uh, you can minimize the usage of magic gate by you yeah, there's still a question of whether you can minimize the usage of magic gate. In particular, one can ask whether you can have a deep Clifford again have a magic augmented circuit, whether you can use that to generate strong design. Okay, so, thirdly and lastly, um, there's a okay. So here I'm talking about generic random uh, generating generating a um, generating a K design that has the same case moment as a random unit as a completely random unitary. But if you you can ask the question, can you generate K design um, of random unitaries that obeys a certain symmetry? This will in many cases this has been shown that you can for if you impose symmetry, you cannot generate designs in a shallow depth. Um, but again, similarly, one can ask whether, although the depths might be a little bit larger, but can you use mainly a Clifford circuit and to achieve those to construct those designs? Um, that's all I want to talk about today. Any questions?
Yeah, Imo, thank you for the very impressive talk. Yeah, any questions?
Okay, Yimu, I have a question on maybe a very early slide. So
Uh-huh.
the comparison between your results and Huang's results on the circuit depth. So I'm a little
Mm-hmm.
confused because I think from yeah yeah this slide. So because these two circuit structures seems to be very similar, except the left hand side we have a random unit, a hard random unitary. The right hand side we have random Clifford. But I'm a little confused because the right hand side seems to have a lower depth, right? So
Yes,
the
yes, yes. Let me
so
explain. Let me explain.
uh-huh,
Yes, yes, yes.
yeah.
So on the left-hand side, this U1, U2, they are approximate K designs with bounded relative error. And so in order to realize a relative error K design, this is yeah, in order to realize a relative error K design, you need a depth that is linear in system size and also linear in K. So each gate U1 will have a say the U1 is acting on Kasi number of qubits. The depth of U1 needs to be proportional to Kasi and also proportional to K. That this is using the this result by Anthony Chen and other people from 2024, second line here.
Uh-huh.
However, on the right-hand side, each V gate is actually a Clifford gate. Actually, it is required to be a Clifford. In this case, um, uh, yeah, it's a Clifford K design. Each V1 is a Clifford K design case, but it doesn't matter what is whether it is Clifford. Yeah, just yeah, V1 is a Clifford gate, and there's a result that any Clifford gate over n qubit can be realized in depth n because the Clifford group has fewer parameters. You only have polynomial many parameters. It doesn't prevent you from realizing any Clifford gate in a linear depth.
Uh-huh. Okay, okay. Thank you.
So V1 is again linear. If you're required geometrically local gates, then V1 has the depth that is linear in Kasi, but it's just there's no additional K factor.
Uh-huh. Okay, okay.
Any other questions? Imo, I have a question. Uh,
Yes,
just
yes.
to confirm, you mentioned in the unitary design, in the state design, for the state design, your construction saturates the optimal bound. Uh,
Mm-hmm.
but that's not the case for the unitary design.
No, 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 no. So so our okay. Yeah, yeah. So most of the problem is is our K scaling is actually very bad. Scaling with K. Okay,
Mm-hmm.
let's go to that. So for example, here we the bad the not so great scaling with respect to K is coming from the fact that we require each purple gate acting on K log K number of qubit to be an exact K design. That require a depth that is 2 to the order K log K. So it's exponential in K.
Mm-hmm.
But the depth lower bound people can prove is actually just log K. So it's just so if you talk about the K scaling, our scaling is very bad.
Mm-hmm. Then is there any way to improve?
Um, I okay. Let me say this. I think uh, our construction is probably not great for large K, and actually the construction doesn't even work for K. So just the CS people care about K that is polynomial in system size even, like poly n. However, our construction of it just doesn't even. Okay, first of all, we are using a result on Clifford commutant. Okay, sorry, that's actually not so important. I think that the thing to say is our construction does not work, only applies to the case that K is smaller than square root of n.
Mm-hmm.
Um, so and if K is greater than the square root of n, actually I don't think the have using this Clifford magic augmented Clifford gate is will buy you too much. I think in that case, the better construction is just probably just using the in terms of depth scaling, it's probably better to use the generic two qubit gate.
Mm-hmm.
So so yeah, I think in short is if you don't care about K scaling, I think our construction is pretty optimal. That means you just consider some finite K. I think it's pretty optimal, and our construction probably doesn't have any advantage if K is too large.
Mm-hmm. Okay. Any other questions? Okay. If not,
Uh, okay, let me
oh,
ask another question. Sorry.
Mhm.
Uh,
Yeah, you can ask
so
many. Yeah, no problem.
yeah, yeah, thank you. So can you give me an example? So for example, if which algorithm I mean, previously I was thinking about classical shadow, but maybe that does not work. So, but then do you have a concrete algorithm?
Oh,
So,
shadow. Yeah, no, sorry. I probably said something slightly confusing. So in
uh-huh.
this shadow tomography, you just start from a state and you apply a random unitary. You want this random unitary to join from unitary three design. Uh,
Uh-huh.
let's see. In that case, in that case, you are saying your circuit is just one step, and
Yeah, but
um,
after that, I mean, after do the measurement, you need to do some reconstruction, right? So the classical snapshot. But in the reconstruction,
mhm.
you contains the U dagger. So I'm not sure whether that part is important or not.
No. This is just guaranteed that. Oh no. This is all about the part before you do measurement. So you prepare a state. You're just comparing two situations. One is your unitary is joined from this ensemble that we constructed for you, or your
Yeah.
unitary is joined from a hard random ensemble. The only thing you can compare is whether. Uh, but I guess in this case, it's there's no your algorithm is just doing nothing except for querying this unitary. There's no W gates are like that doesn't really exist. And let's see.
Yeah.
Yeah,
Yeah.
maybe this is not a good. Yeah, so this is not good. So you want an example that you actually use a multiple copy of U. Is that correct?
Yeah. Or maybe a single copy of all U is also okay. I mean, is there some uh, concrete protocol that uses either single copy or multiple copy that can be replaced that the hard random unitary can be replaced by this approximate uh, unitary. I
Oh,
mean,
oh, then for example, uh,
guaranteed by this inequality. I mean,
guaranteed by this inequality.
yeah, because when I consider about the problem, it looks like we can do some measurement of all talk, or but that also contains
Oh,
backward evolution,
oh,
something like
oh.
that.
Oh, maybe one thing is you can consider a flow-case system that every time step you apply some random unitary. They
Oh,
say um, that would be one example if you
like a measuring some two-point function of some quantum dynamics.
yes 2 point
Okay.
no sorry,
Uh-huh.
sorry, sorry. Yeah, 2 point two point function is fine. Yeah, 2 point function is fine. You just yeah for example like that. Yeah. Say you
Mhm. Okay.
evolve it for t step and measuring the autocorrelation function.
Uh-huh. Uh-huh. I see.
Um mm,
Uh-huh. Okay. Okay. Thank you.
yeah,
Thank you.
they're not really. I have to say, me personally also struggle thinking about the application, like the existing application
Mhm.
of the unit gate.
Mhm.
Mhm. Any further questions? Okay, if not, Yimu, thank you for the very impressive talk.
Thanks for inviting me.
Thank you. Thank you.
Bye.
Okay, bye.